All right, section 6.1, we were working on last time, the set of rational numbers, and we were comparing fractions, basically, right? We got into the point where we had looked at different ways to compare fractions. Are they equal? Which ones are bigger? And so forth. And we had 4 methods in which to do this. And we are encountering this problem right here, where we are asked to figure out which of the 3 symbols goes correctly between the 2 fractions. So before we write anything down, just to help me remember, you tell me what you remember. What are some of the ways? What is one of the ways of comparing fractions? What could you do?
The least common denominator.
All right, we could get a least common denominator between the 2 fractions. That's one of them. Good. What else?
Reduce them.
We could reduce them to getting something in common still, right? We're still looking for something in common. So least common denominator, maybe just a common denominator. Maybe it's the least, like reducing it down to something that's in common or increasing it something. So we've got least common denominator, we've got common denominator. We can do the cross multiplication. That was one of them, to cross multiply. You guys remember the 4th option? Maybe the 4th option was reduce. Is that what I said my 4th option was in the one a bit before? Maybe I did. Let's see how I wrote it. Reduce, yeah, so reduce and common denominator. So reduce is the one you said. Common denominator is the one that I was saying. Okay. So those are our 4 options. When you're actually looking at 2 problems in particular, like this one, you can probably also sort of look at it and sort of make an educated guess as to which direction it should go. So we're going to educated guess this, and then we're going to do it using one of those other methods to check to make sure that we actually are thinking about it correctly. The first one is 21 over 430, and the second one is 51 over 250. Can you make an educated guess as to which one should be bigger? Okay, why do you think that one's correct, Madison?
It's a bigger number than compared to the other one.
Yeah, so the numerator's bigger. So a bigger numerator often means a bigger fraction, right? Not only that, but the denominator is also smaller. So when you divide by something smaller, you also get a bigger fraction. Okay, so those are both good things. So we expect that the one on the right is bigger. The other thing we could do if we weren't so sure and we wanted to sort of approximate it is we could take the values and we could round them to something close but easier to compare. So you could do something where you said, okay, well this is about 20 and this is about 400 and this is about 50 and this is about 200, right? And then because they're zeros, we can divide them out. So this 0 and this 0 reduce, and this 0 and this 0 reduce, and then we can actually reduce the 2 and the 4, and we end up getting 1 over 20 on the first one, and we get 1 over 4 on the second one. And these aren't exact, right? It's an approximation, but it gives us some kind of an idea of what to expect. Which number is bigger, 1 over 20 or 1 over 4? 1 over 4. Okay? Let's try, so this would sort of be an approach to think of it as an approximation. I'm going to move this over on my slide. This is a way of approximating. You do have to be a little bit careful with approximating. We sort of, made our own decision on what to change things to. If you're careless or just not careful enough, sometimes you could actually end up with a wrong answer. But these fractions are pretty far apart, actually. So we feel fairly comfortable this is probably right. If we want to check it exactly, one of the methods somebody had just said was cross multiplying. So let's try to do it exactly with cross multiplying. And then we're going to try it with a common denominator or a least common denominator, just to see that it is in fact the correct answer. And if you're not given the expression as to why, right, like as to how you have to do it, you get to pick how you do the problem. So it's not a big deal to me unless they tell you or I tell you, do this with cross multiplication. Then you can choose, okay? So if we cross multiply this, we'd have 21 over 430, and we'd have 51 over 215. And the question is what goes between them, right? So what 2 numbers would I multiply? Right, 21 and 215. So do 21 times 215. And again, we're questioning what in the world is between them. And then the other 2 that I would be multiplying are what? Right, 51 and 430. So just for fun, let's actually do the multiplication. What do we get when we multiply 21 times 215? I'm glad to see some calculators today. That's good. What'd you get?
21 times 215 is 4,516.
Awesome. And someone else, what is the 51 times the 430?
21,000.
Like nowhere even close, right, to the other number. Significantly larger. So this is definitely the larger value down here on the right-hand side, which means it's the larger value up here. So that's the correct symbol. Let's try it one more time with a different way, and let's do least common denominator. I kind of like least common denominator approach on this one. Any idea why, looking at this might be a good approach for this one? Right. 215 is half of 430. Or you could say that if you multiply 215 by 2, you get 430, right? So they're easily obtained. Those common denominators are easily obtained. So this is 21 over 430 on the left. That one didn't change. And then I have 102 over 430 on the right. Very quickly, we can say that the one on the right is larger, which means 51 over 215 is larger than 21 over 430. So this is, in fact, the right answer in the middle. And any one of those options would be a justification as to the why, and perfectly reasonable justification. All right. Interesting idea. One of the facts that is true about rational numbers is that they are a dense number set. What does that mean? Well, dense means that if you are given any two numbers, there's always a number between them. So this is not true for every number system. If we were dealing with whole numbers, right, 1, 2, 3, 4, 5, and so forth, that kind of numbers, it is not dense because there are no whole numbers between 1 and 2, between 7 and 8, right? So whole numbers are not dense, but rational numbers are. Rational numbers are dense. So this is Theorem 6.4. It says that that is actually a true statement about rational numbers. And other number systems don't always have that problem. So then you might start asking the question, well, how do I find that number that's in between them? And there are several ways to do it. You can add the two numbers together and divide by 2. That will always work. You can do that. But there's actually a really cool, clever way to do it too. And it's this one right here. So this is Theorem 6.5. It says, if you have two rational numbers, a over b and c over d, and they have positive denominators, okay, so if the denominators aren't positive, if they're negative, make the numerator negative instead. So keep the negatives on top. Keep the negatives off the bottom. Whichever number is smaller, we're going to write on the left, and whichever number we're going to write on the right, the larger number. Then one number that will be between them is the number that happens when you simply add the numerators together, and you divide that by the denominators added together, which is a lot easier, usually, than adding the two numbers together and dividing by 2. Not always, but a lot of times it's very, very straightforward. So here's an example of one of those. 33 over 427 and 7 over 92. If you were to have to add these two numbers together and divide by 2, that would not be easy, because the denominators are not the same. You guys with me? So we haven't done this yet in this class. We will, but you'd have to get a common denominator, right? And those are not especially pretty numbers, 427 and 92. I mean, really? I don't want to get a common denominator between those two. And then when I divide by 2, that also might end up making denominator issues, because I'm going to be dividing a fraction by 2. And if the numerator is not even, that means I'm going to have to do something weird with the denominator. I mean, it's not a simple process. But this process from Theorem 6.5 is very simple. What does it say that I would need to do to find the number between these two? Add the 33 and the 7, good. And then what?
Divide it by 427 plus 92.
You got it. And that is all whole numbers, right? That's a beautiful thing. So much easier than what we just described before. So what is 33 plus 7? 40. And what is 427 plus 92? 519 is correct. And then we would look to see if this would reduce, okay? So what kinds of numbers divide the 40? I'm using the 40 simply because it's smaller. It's easier to think about. What numbers divide 40? 10. Does 10 divide the top and the bottom here? No. What else divides the numerator? 4. Is 4 going to divide the denominator? No. What else is dividing the numerator? 2, or 5, or 8. None of them are going to end up working. So we're going to check through sort of a list of numbers that would try to divide that numerator, and if we don't come up with anything, then this is going to be in reduced form. So here we go. This is the number that's between these two numbers. All right, so the question to ask then next is, why must there be a number between these fractions?
Because it's a dense number, or no, it's like the dense the property.
Right. It's because rational numbers are dense. That's that Theorem 6.4 that we kind of 2 slides back encountered, right? They're dense. They have this property. These two numbers, 33 over 427 and 7 over 92, they're rational numbers. So they fit in with this description. Now let me describe it a little bit intuitively, and that might help you too. Because you might be saying, okay, but that's just saying that theorem. I'm just saying that theorem again. And you're right, I am just saying that theorem again, and it is true. But if you want to think about it in a little bit different way, this might help you. These are two numbers, which means they are on the number line, right? I don't know where they are. I don't even care where they are, but they're on the number line. I don't even know which one's smaller, to be honest. I think I have it written down. No, I don't. I don't have the number even written down. But one of them is the first red dot and the other one is the second red dot. Are you with me? Okay. So there is the possibility that any time, and this doesn't go back to why this process works particularly, but why the other one does. So if you were to add the two numbers together and divide by 2, what would you actually be finding? Do you know? The average. Where would it be on the number line? Exactly in between them, right? Halfway. Sometimes we call it the midpoint. You guys remember the word midpoint? So it would be finding the exact halfway point in between them. So if I have the ability to always add two numbers together and divide by 2, then I'm always able to find a number in between two rational numbers.
So
I always have that ability.
How can you easily tell if the number's rational?
A rational number.
If it's a fraction?
If it's a fraction, where you can write the numerator and the denominator as whole numbers.
Okay.
Or negative. I mean, they can have negatives. There's nothing wrong with
But
that.
it's like, it can't be like 4.5 over.
That would be okay, because watch what you can do. 4.5 over what?
3.2.
Sure. Is there any way to change this so that the numerator and the denominator would be whole numbers? You can move the decimal. Do you remember why you can move the decimal? And what you're actually doing when you move decimals is you're multiplying by 10. If you multiplied by 10 on the top and the bottom, this would turn it into 45 over 32.
So if you can do decimals, what would not be rational numbers?
We encountered one last time where we talked about it. Does anybody remember?
Pi.
Pi,
Okay.
that's an example. Square roots.
Okay.
E, if you've encountered E before,
Okay.
those kinds of numbers. Yep. Okay. Here we have a student, and they've simplified some work. You're going to have students like these. Maybe you have been a student like these, and that's okay. They've taken the fraction m plus n over p plus m, n, I said it wrong, p plus n, and they've reduced it to m over p. So we're going to do what you should do as a teacher if you saw a student do this. The first thing you really should ask yourself is, what did the student do? So what did they do? Yeah. They probably even used that word when they did it. Say it louder.
Canceled.
Canceled. They did something called canceling, right? All right, so they canceled. the ends. If you asked them, that's probably the word they would use too. They would probably say, I just canceled the ends. Right? If they drew it on the picture, they might even draw this. Right? You might see that happen. Why do you think they might have done that? Why would they think that that's a valid operation?
Because when you're like dividing stuff like, or where there's like a number over a number, if they're the same, in different types of equations, you can cancel them out.
Okay. Do you remember in what types of equations? Multiplication. Can we do this if the numbers were multiplied? Yeah, we can. This operation works if everything were multiplied on top and multiplied on bottom. So that's probably where they're getting that notion from, is this idea of multiplication. So I'll write it out the way that they might be thinking about it. Screen doesn't want to write very well today. Okay, because of multiplication properties. So they're probably thinking of something kind of like this. The letters I'm using, M, N, over Pn, like this, which is the multiplication version of this. And can I do that here? Yeah, I can. That's actually just simplifying or reducing fractions. That's what they're doing on that property. Now here's the question where you get to really think about as a teacher. So what would you do to show the student that this process does not work? I mean, we can tell them, oh, no, that works for multiplication, doesn't work for addition. It's kind of like saying the denseness thing over there. Oh, yeah, it works because the property is dense. But how would we explain as the why? Do you have an idea? I think that's a good idea. Do you want to give me some numbers?
5 plus 7 divided by 3 plus 8.
Well, we want the last one to be the same, so I'll leave it as 7. But the other numbers will work just fine. So what did we say? P was 3. So if we actually simplify this, as in we add the numbers together first and do that, we would get 12 over 10, right? Okay. This reduces, so it'd probably be a good idea for us to reduce it to talk about it in a moment. So this would be 6 over 5, because the top and the bottom both divide by 2. If we followed their train of reasoning down here, we would cancel the 7s, right? Which would leave us with 5 over 3. And then think with me for a moment, how can we justify that 5 over 3 and 6 over 5 are not equal? And that's what our goal is, right? Our goal is to show them that these do not create equal values.
You have to have a common denominator.
That'd be one way we could get a common denominator. What else? We get a least common denominator, which would actually probably be the common denominator in this case because these fractions are small. We could do cross multiplication, right? And these are already reduced, so that's not an option for this particular situation. But those are the 3 ways that we could verify to the student that these are not the same fraction. We could also talk about the fact that since they're in reduced form, that is, I can't reduce 6 over 5 or 5 over 3 to anything smaller. There's the smallest they can get. They clearly, if they're the smallest they can get, can never be the same because they're not the same right now. So we could also justify it sort of in language that way. Lots of options because students think about things in different ways. Okay, last example in this section. We're going to take a set of numbers equivalent to 1 over 3, 1/3. And we're going to graph them as points on an xy axis so that the numerator becomes the x coordinate and the denominator becomes the y coordinate. And we're going to talk about the kind of graph that we get. So what is it describing? Well, it's saying that the numerator, what's the numerator in this fraction? It's the 1, right? It's going to become the x coordinate of an ordered pair. And the denominator, the 3, is going to become the y coordinate in an ordered pair. So this is the 1 point that they give us, 1, 3. We're going to plot this on an axis. But we need to plot other points as well that have fractions equivalent to 1/3. So I'd like for us to generate a few options. I don't want them to be large because I don't want my graph to get so huge that it's difficult to draw. So think small. So somebody give me one of them. 2/6 would be an option. So if I did 1/3 is my fraction, and if I did 2/6, that would be the same, and that would give me the value 2/6 as a point. Another one. 3/9 would work. That is as large as I'd like to go. Can anybody think of another one without getting any larger? I don't really want fractions either. How about that? Is that equivalent to 1/3? It is. What ordered pair does it give me? -1, -3. So we're going to take these 4 points, the original 1, 3, and then the 3 that we just created, and we're going to put them on an XY axis. Okay, so draw yourself a graph. And we're going to plot these points. So we have 1, 3, 2, 6, 3, 9, and -1, -3. What kind of a graph is this forming? It's linear. Yeah, it's linear. Do you guys see it? I was kind of snotty and I told you I don't want fractions, but could I have fractions? Yeah, I definitely could have a fraction that would work here. What would it be? Or at least what would a potential one be? Well, I mean, like I chose to use, 1/3 and 2/6, but what if I did like 1.5 over 4.5? That actually would work. I would just be multiplying the numerator and the denominator by something that was fractional instead of something that was a whole number. I could do that. So this becomes a line. There is a problem though. It's not exactly a line. Any idea why it's not exactly a line? Okay, let me ask that question in a minute. Let's ask a different question. What is something specific about this line that you can tell me? What kind of things tell us how lines look? There's a couple of specific things. Can anyone think of an equation of a line, a general equation of a line that you know? Y'all are scaring me. General equation of a line. Yeah, what would it look like? You got it. Yeah, I know you guys know this. All right, y equals mx plus b. The two specific things in this equation, this is the one that I was referencing to, it's helpful, are the m and the b. Do you remember what m stands for? Slope. What's the slope of my line that I've drawn here? Can you tell? Yes. What does the b stand for? The y-intercept, where it crosses the y-axis. What would it be here? Okay, it would be the origin, right? And we've got a problem right there. What is the ordered pair at the origin? 0, 0. What were my points supposed to be? Numerator and denominator create the fraction 1/3, right? Does 0/0 do that? No, it does not. So that actually runs us into a problem. Not a problem so much as it has to be that we have to exclude that point. So this is a line with the slope 3, but not including zero, 0. So in terms of my graph, what would be best to draw is to draw a hole there. There is the ability to get as close as I want to that point, but there is not the ability to actually equal the point 0, 0. Any questions on that?
So we can't do 0, 0 because it messes up the
Right, because that's where the points were, the ordered pairs we were creating were supposed to have come from to begin with. All right.